We'll use the Laplace transform to solve the initial value problem y double prime plus y is equal to delta of t minus 2 pi plus delta of t minus 4 pi with the initial conditions y of 0 equals 1 and y prime of 0 is equal to 0. Remember that the Laplace transform of delta of t minus t sub 0 is equal to e to the negative s times t sub 0. Usually when we have a transform, we have an inverse transform. But this one acts a little bit different because remember the inverse Laplace transform of e to the negative as times f of s is equal to f of t minus a times the unit step function of t minus a. So the delta function gives us an e to the negative s with a number. But the inverse transform of an e to the negative as is going to be the unit step function. This should make sense because the delta function was, originally defined in terms of the unit step function. With these two facts in mind, the transform and the inverse transform, I'd like for you to solve this initial value problem. The transform of y double prime is s squared y of s minus s y of 0 minus y prime of 0, and sy of 0 gives us just s because y of 0 is equal to 1. The transform of y is y of s, and on the right-hand side, the transform of delta of t minus 2 pi is e to the negative 2 pi s, and for delta of t minus 4 pi, we have e to the negative 4 pi s. We can collect our like terms of y of s. After collecting like terms and factoring out y of s, we have s squared plus 1 on the left. We've added s to the right-hand side. The rest of it hasn't changed. Dividing by s squared plus 1 gives us s over s squared plus 1, and then the e to the negative 2s over s squared plus 1 and e to the negative 4s over s squared plus 1. All terms are positive. The inverse transform then, s over s squared plus 1 transforms to the cosine of t. For e to the negative 2 pi s, remember that's going to give us the unit step function of t minus 2 pi times the sine of t is what I've written. And then e to the negative 4 pi s, again, u of t minus 4 pi times the sine of t, because remember that the sine of t minus 2 pi and the sine of t minus 4 pi are both the sine of t because of the period of the sine function. Next up, y double prime minus 7y prime plus 6y equals e to the t plus delta of t minus 2 plus delta of t minus 4. Our initial conditions, I always like this, y of 0 equals 0 and y prime of 0 is equal to 0. Go ahead and work this out and then come back. It kind of looks like a rainbow burst out over my screen here. For y double prime, we have s squared y of s, minus 7y prime is going to give us minus 7s y of s, and plus 6y is going to give us plus 6y of s. E to the t on the right-hand side transforms to 1 over s minus 1, and then delta of t minus 2 and delta of t minus 4 give us e to the negative 2s plus e to the negative 4s. Factoring out the y of s on the left and then dividing by the s squared minus 7 minus 6 also factored gives us y of s is equal to 1 over s minus 1 quantity squared times s minus 6 plus two terms both with denominators of s minus 1, s minus 6. One numerator is e to the negative 2s, one numerator is e to the negative 4s. Those exponentials have nothing to do with each other and so should be separated for the duration of this process. That first fraction decomposes into a over s minus 1 plus b over s minus 1 the quantity squared plus c over s minus 6. The second and third fractions decompose identically the same. We have two denominators. It's a over s minus 1 and then b over s minus 6. Those processes don't have anything to do with each other either, so it's two separate full processes. After finding our constants for both of these processes, we get that y of s is equal to negative 1/25 over s minus 1 minus 1/5 over s minus 1 quantity squared plus 1/25 over s minus 6. Moving on, plus we've got an e to the 2s times the quantity 1/5 over s minus 6 minus 1/5 over s minus 1, and then plus e to the negative 4s with an identical set of parentheses there. The inverse transforms then are negative 1/25 e to the t, and for the denominator s minus 1 quantity squared, that transform is t e to the t. So we have negative 1/5 t e to the t plus 1/25 e to the 6t. And for the remaining terms, I factored out the 1/5. We have from e to the negative 2s, u of t minus 2, and it's multiplied by e to what would be 6t, but the argument needs to match the u of t minus 2. So it's e to the 6 times the quantity t minus 2 minus e to the t minus 2. And similar expressions exist, u of t minus 4 with a 1/5 out front, e to the 6 times the quantity of t minus 4 minus e to the t minus 4.